Alright, this video is covering section 2.1 from OpenStax Calculus Volume 2. At the bottom of every page is actually a link where you can go to download the textbook itself if you want to see that material. That's where all my problems are coming from, except maybe a couple, but for the most part they're all coming from that book. So, section 2.1, area between curves. Alright, so what we're going to consider at this point is finding the area between two functions, f of x and g of x. f of x and g of x. Alright, so if they are two continuous functions over an interval from a to b, a closed interval, such that f of x is greater than or equal to g of x. So we have f of x is above g of x on that whole interval. Now we want to find the area between the graphs. This is going to go in the same pattern, in the same manner that we determined the area underneath the curve. Because really what we were doing there, when we say the area underneath a curve, is we're finding the area between two functions over an interval a to b, and that area is between the function f of x and y equals 0, g of x equals 0. Okay, so this is just the more general case for what we've actually already done. All right, so if we have these, we are going to have to start out by breaking up this region into representative rectangles, kind of like we did with Riemann sums, because this is actually going to be a Riemann sum. All right, so in this case, this region is going to be represented by rectangles that look something like that. Okay, so if we broke this up into n rectangles, each one would look something like that. Now, we need to find the height and the width of each of these rectangles. So the delta x, okay, that is going to be from here to here. So that is going to be broken up, if we have n rectangles, this is going to be b minus a over n. Easy enough, same way we did before. Now the different part's going to be the height of that rectangle. The height of this rectangle is going to be, because f of x is greater, this is going to be f of x minus g of x. Now for our ith rectangle, this will be g of x, f of xi minus g of xi for the ith rectangle there. Okay, now this yields a summation for our area. We just said we have going from I equals 1 to n rectangles. This would be the height times the width. Okay, so delta x times h, which in this case is f of xi minus g of xi. That is our summation. That is our Riemann sum. Now, if we take the limit as n goes to infinity, the number of rectangles, as we have more and more rectangles, we see this actually gives us this integral formula. The integral from a to b of f of x minus g of x dx. So here's our theorem for this. The area between curves. Let f of x and g of x be continuous functions so that f of x is greater than or equal to g of x over the interval a to b. Let R be that region, the region bounded by the two functions between a and b. Then the area is given by a equals integral from a to b of bracket. Okay, this is quantity here. F of x minus g of x dx. Keep that in mind. We need to make sure we are subtracting the two functions, that's the height, and then integrating. Okay? And there is the website to get the textbook from if you'd like to. All right, now we are going to use this function a whole lot. All right, so find the area of the region bounded by f of x equals x plus 4 and g of x equals 3 minus x over 2 over the interval a, b, which is, in this case, 1, 4. Now, first thing I want to do is actually sketch this, because that'll determine which one is on top, and which one's above, and which one's below. All right, so x plus 4 will start at 4, increasing by 1 each time. Okay, so we have something that's going to look like that. Now we have 3 minus x over 2. All right, now this is a negative slope here. Okay, so it really doesn't matter how good my sketch is, because I know I'm going from 1 to 4. Now let's see, 4, at 4 this function would be at 1, and at 4 this function would be at 8 if this were completely accurate. Alright, so we are integrating from 1 to 4, so our area actually looks something like this. Right, now, because our f of x in this case is actually above, now the stipulation of our theorem was that f of x is greater than or equal to g of x. In this case, based on our graph, that is very true. So we can find the area is going to be the integral from 1 to 4 of f of x minus g of x. F of x is x plus 4 minus 3 minus x over 2 dx. So combining some terms there, go from 1 to 4 of 3 over 2x plus 1 quantity dx. That is going to be x squared, if we take the antiderivative, x squared, and that is 3 over 4 x squared plus x evaluated from 1 to 4, which is 16, if we plug in 4 there, yep, minus 7 over 4. If we do that calculation, we get 57 over 4. Now, because this is area, kind of neglected doing this in the past, but I'm going to go ahead and say units squared. That'll be important in the next couple of sections. Okay, example 2. Find the area of the region bounded by f of x equals 9 minus x over 2 squared and g of x equals 6 minus x. Sketch the region and find the intersection points. So we aren't actually given the interval, but we want to know the region that's bounded by those two. So if I graph this, I'll need a little bigger than that. Alright, so I'm going to go ahead and do 6 minus x first because I know that it's going to be at 6 and it's 6. Let me get it that way. Okay. Now, the value at 6, let me just go ahead and plug 6 into f of x. Plugging that point in there, I get 0 actually. So my f of x is 0 at that point. Its y-intercept is 9. Okay, and let's see, that is going to turn around there. That is actually the vertex, so it's also going to hit at -6, and it's going to curve down this way. Alright, so what I really need to know is where these two intersect. Okay, well, if I set those two equal to 0, okay, I would determine these actually intersect at -2. So the region that I am determining the area of is from -2 to 6 of, now let's see, f of x is above, which is our stipulation, so this is 9 minus x over 2 squared, I'm going to have lots of parentheses here, minus 6 minus x dx. Alright, now this will work out to be 1/4 x squared plus x plus 3. Yep. And that should be a -1/4 actually. That's 1/4 negative, and then we have plus x, yes. Alright, and that is the integral from -2 to 6 dx. So -x cubed over 12 plus x squared over 2 plus 3x evaluated from -2 to 6 is 18 minus a -10 over 3. So I'm plugging 6 in there, plugging -2 in, and I get a total value of 64 over 3 units squared. Okay, so sometimes we do have to find the intersection points. Okay, in that case, we can use technology. We can use our 83, 84, whatever calculator we've got, Casio if you have that. You can use that to find the intersection points. You could also set the two of them equal to 0. Now that would have been a little bit more complicated here, but it could be done. So sometimes we need to find the intersection points if we don't know what they are. The sketch that we have to make generally helps out quite a bit. So on example 3, find the area of the region bounded by f of x equals x and g of x equals x squared, x to the fourth actually. Sketch the graph of the area. So the first thing that I want to do, f of x. Okay, now I don't know exactly what g of x looks like, but I do know that its y-intercept is 0, and that it is going to look something like a quadratic. It's going to have a sort of a U shape to it. And in this case, it looks something like this. Because at 1, the value is 1, which is perfect because that's the two places intersect there. We intersect at 0 and at 1. So the region bounded by these two functions is that little region right there. So this is, the area is the integral from 0 to 1. Now, the upper function is f of x equals x. So x minus x to the fourth. So this would be integrating these two. That is x squared over 2 minus x to the fifth over 5 from 0 to 1. Now, plugging 1 in here is easy enough. Okay, 1/2 minus 1/5. Okay, which is 3/10. Minus plugging 0 in there, we get 0. So the answer here is 3/10 units squared. And of course, pause here, go back, see if there's something that doesn't quite make a whole lot of sense. If it doesn't, you can always ask me. That's kind of the point of being an instructor. But pause these things, go back, make sure the calculations make sense. Don't just trust what I've got. Okay, I've checked my work a couple times. I've actually worked the problems out twice now. But still, you never should just trust what you see. It should all logically make sense to you. If it doesn't, then you need to ask questions and figure out what doesn't. And if something's wrong, something's wrong. Okay, so the next logical place we go from here is, what if f of x greater than or equal to g of x is not true? Then we have to figure out where they intersect, which is what we actually had to do earlier, and we inspected them and said, okay, which one is bigger? Well, what if they're not always one on top, one on bottom, okay? What if one of them is not always greater than, and one of them is not always less than? Well, in this case, we need to figure out, we still need to do the difference, but it's the absolute value of the difference. That way, we're taking whichever one's bigger actually comes out on top. Okay, so I'm just going to write this here. If f of x is greater than or equal to g of x, then this actually just becomes the integral from a to b of f of x minus g of x, which is what we had earlier. Okay, if f of x is less than or equal to g of x, then this statement comes out to be integral from a to b of g of x minus f of x dx. So in either case, we have the upper function minus the lower function. All right, so, but if we're not told the intersection, we need to figure out which one is on top at which point, which one's above at which point. So example 4, find the area of the region bounded by f of x equals sine x minus cosine x. Because f of x is sine x, g of x is cosine x over 0 to pi. So if I graph this, so 0, we have sine. Okay, so sine at pi, okay, we have got, that's actually just that first half. Okay, cosine x starts at 1. Okay. So in this case, we have two areas we need to calculate. We have this one, and we have this one. The first region, okay, is going to be the integral from 0 to wherever they intersect, which I do know for a fact using technology that's going to be pi over 4. And that is, cosine is above, so we have cosine x minus sine x. Okay, that's our area 1. Area 2 is from pi over 4 to pi, and it's sine x minus cosine x, because it is reversed. And there we have the sine is above, the cosine is below. Alright, so that would turn out to be, let's use this space over here, this would be negative sine x minus, no, actually it's just plain old sine x. Sine x plus cosine x, evaluated from 0 to pi over 4. And this one would be negative cosine x minus sine x from pi over 4 to pi. Now, evaluating each one of them separately. Okay, area 1 is equal to the square root of 2 minus 1, and area 2 is equal to 1 plus the square root of 2. So combining those two, our area is 2 square root of 2 units squared. Next, we're going to do the same functions, different interval. Alright, so the sketch of my graph for sine x, now this is from pi over 2. Pi over 2 to 2 pi. Alright, so in this case, pi over 2, so sine, there's pi, but we're going to 2 pi. Alright, and cosine, okay, so this area is going to break up. So here's pi over 2, highest point there, pi over 2 to 2 pi. So we need a couple of regions. So this is going to be the integral of pi over 2 to, in this case, 5 pi over 4 is where those two intersect. Of, and that would be sine minus cosine dx plus 5 pi over 4 to 2 pi of, in that case, we have cosine is above, so cosine minus sine x dx. Okay, now these integrals are going to be the same as before, they're just going to be evaluated differently. So this is negative cosine x minus sine x pi over 2 to 5 pi over 4, sine x plus cosine x, evaluated from 5 pi over 4 to 2 pi. Okay, so we get square root of 2 plus 1, 1 plus square root of 2, which, that's great, those are the same. So our area is 2 plus 2 square roots of 2 units squared. So finding that intersection point, again, I can't say it enough. Use technology, the graphs. Okay, you can actually make a good estimate just from our sketches, because we have pi over 2, there's pi. You know, we can actually make some good determinations in there. All right, now find the area of the region R. Okay, well, in this case, it's going to break up into two regions. This is the area underneath x squared from 0 to 1. So from 0 to 1 of x squared dx. But we also have the area underneath from 1 to 2 of 2 minus x. Alright, well, that'd be x cubed over 3, 0 to 1, which is actually 1/3. Plugging 0 in does nothing. And the second, let's see, we have 2x minus x squared over 2, evaluated from 1 to 2. Well, plugging 2 in, we get 2. Plugging 1 in, we get 3 over 2, so this ends up being 1/2. And so our total area there is 5/6 units squared. Okay. Number 7. Find the area of the region. Apparently I left off all these A's. Find the area of the region R. In this case, same idea. It's the area underneath x, the square root of x. From 0 to 1, it appears to be the intersection there. Dx plus the integral from 1 to 3 of 3 over 2 minus x over 2 dx. Well, that first one is going to be x to the 3 over 2. And we divide by 3 over 2, so 2/3. From 0 to 1. It's easy enough. That is going to be 2/3. Plugging the 0 in, nothing, so 2/3. Okay, that'll be 3 over 2x minus x squared over 4 from 1 to 3. Plugging 3 in, we get 9/4. Plugging 1 in, we get 5/4, so that is just 1. So our total region is 5 over 3 units squared. Okay, now at this point we've really covered everything we need to cover. Alright, so we do have a couple more problems though. Okay. These are going to have us think a little bit differently. So the method that we just are doing, okay, we have two integrals if you notice. It often involves two because the intersection points we change the above or below functions. Okay, so in order to simplify this, we often can integrate from right to left. Alright, so if you can imagine this region right here, okay, but we're going to integrate with respect to y. Did I have a picture in here? No, I didn't. Okay. So if you can imagine rotating this sideways, okay, thinking from left to right. So here would be my rectangle. In this case, the upper function is g of x, and the lower function is x squared, and that's it. The problem is we have to think of these in terms of y. So I'm going to call these, I'm going to rename this, let's see, I'll go with h of y for this one. And I guess I'll go with j of y. Right, so h of y is going to be equal to the square root of y. That is the inverse function of x squared. J of y is going to be 2 minus y. Because again, that's the inverse function. So just to refresh you there, if I said y equals 2 minus x, and I solved for x, in this case, I could get x equals y minus, or no, it'd be 2 minus y there. So then this is g, or in my case I called it j. J of y equals 2 minus y. Okay, so that's how we go about doing that. But this actually simplifies it a little bit, because this becomes the integral from the y values are 0 to 1. Again, if you kind of turn your head to the side 90 degrees, you can kind of see it goes from 0 to 1 in the y values. That region, I'm going to do this. That region goes from 0 to, yeah, it intersects at 1. So really it's from here to here, this region right here. and the function farthest to the right is 2 minus y. Minus y minus the square root of y, and I need a bracket there, dy, because the change is actually in y in this case. So this would be, go ahead and, I'm going to go ahead and integrate. This would be 2y minus y squared over y minus y to the 3 over 2, and it's 2/3 y to the 3 over 2. Integrated from 0 to 1. Plugging 1 in, we get 5/6. Plugging 0 in, we get 0. So this is 5/6 units squared. Now, I just want you to look back at number 6, because we're on number 8. Look back at number 6. The answer there was also 5/6. And it was the same region, except in doing it in one integral, we did it in 2. So you can kind of see what's going to happen there. These often work out where they are going to be the same answer, but it might be a slightly easier way to look at it. All right, so number 9 is also going to be like number 7, actually. It's the same functions, actually. So we need to find the inverse functions, and I'm going to go ahead and use different functions here. I'm going to say g of y. Well, I guess I can do this. This is going to be slightly ambiguous, so forgive me, I guess. F of y, the inverse of square root of x is y squared. And the inverse of this one right here is going to be g of y is negative 2y plus 3. So if I set that equal to y, just so you can see my logic here, multiply through by 2, so that'd be 3 minus x equals 2y. Subtracting 3, and then dividing by negative 1, x is negative 2y plus 3. So in this case, the function to the right is the g of y, and the lower function is the y squared, and we're going from 0 to 1. So the integral from 0 to 1 of negative 2y plus 3 minus y squared dy, which is, if we take the antiderivative here, negative y squared plus 3y minus y cubed over 3 from 0 to 1. Plugging 1 in, we get 5/3. Plugging 0 in, we get 0. Okay, now if you compare that side by side with number 7, kind of depends on how you look at it, but in some ways I think this actually might be easier if you can change your perspective to thinking in terms of y instead of x. Okay, that is the end of this section of area between curves. So go on, you can do your homework now.